The extra credit physics lecture that I chose to attend was entitled What Happened Before the Big Bang, given by Martin Bojewald from Penn State University on April 8th, and was hosted by Pablo Laguna. This lecture was part of a series of lectures known as the Physics Colloquium. Unlike other extra credit lectures offered this semester, this lecture was based on new theoretical physics, directed to the peers of the presenter, including doctors and graduate students, who are participating in fields related to the ideas presented in the lecture. This makes it difficult for a first-year physics student to understand the complex physics and math involved in the ideas presented in the lecture. Studying modern cosmology suggests a phase of the universe known as a hell state with infinite temperature, max ignorance, and no spatial expansion. This is considered as a singularity by the theory of general relativity. The presenter, Bojewald, suggests that looping quantum gravity could be used to resolve the idea of this singularity. The use of this method has many surprising results on quantum spacetime that affects both mathematical models and our concept of modern cosmology, the understanding of which can be developed and described through complex mathematical equations. The physics involved with examining this singularity and looping quantum gravity require an advanced knowledge of both physics and calculus, something which I do not yet possess, but attending this lecture has prompted me and sparked interest to learn more advanced calculus and physics and learn more about other theoretical ideas about physics. In the presentation, it was stated that loop of quantum gravity had magnetic flux holonomy along loops in space tangent t, and that in the beginning of the universe there was only four-dimensional space, and that space-time extended across the Big Bang with a mix of cyclic and linear views, and that after the Big Bang there was essentially a clean slate with no growth of entropy. Even with my limited knowledge of the physics and calculus used in this lecture and looping quantum gravity, I still managed to learn a few things that were very interesting to me. One thing was that it is possible to use very complex equations to possibly predict what occurred before the Big Bang. To my surprise, it is possible to use ideas predicted by Einstein to predict what occurred previously to the Big Bang, ideas that were developed many years ago. I also learned that it is possible to use quantum gravity looping to explain singularities encountered in modern cosmology, a process that uses complex algebra and discrete geometry to examine spacetime and the wave functions of the universe. After overcoming the initial shock of the extremely complex equations and ideas presented in the lecture, I began to enjoy and even somewhat understand the math and theoretical physics involved in the lecture. I would be interested in learning how the concepts we have learned in class, such as the energy and momentum principles, apply to the physics discussed in this lecture. I have always had a fascination with theoretical physics, from string theory to the origins of the universe, and attending the lecture has really introduced me to some of the ideas involved in it, as well as the math. I doubt this will be the last lecture about theoretical physics that I will hear while I'm at Georgia Tech.